All right, let's get right into it. I mean, we're surrounded by concrete pretty much everywhere, but have you ever stopped to think about what it actually takes to trust it with our lives? Well, today we're going to go inside the lab and see exactly how engineers destroy something, all in the name of keeping us safe.
I mean, it's a huge question, right? When you're looking up at some massive skyscraper or driving over a giant bridge, what's the one thing that's actually stopping it from all coming crashing down? You might think it's some super advanced computer or just a brilliant design, but the real answer? It's way, way smaller and a lot more hands-on than you'd probably guess. It all boils down to this: a simple 150 millimeter cube of concrete. Yep, this little block is basically the unsung hero of our story. The safety of these enormous structures, it all rests on what happens to thousands, and I mean thousands, of these little cubes in labs all over the world. And this happens way before a single steel beam is ever put in place. So why all this fuss over one little block of concrete? Well, it gets right to the very heart of what civil engineering is all about, and the massive, massive responsibility that comes with it. I mean, just think about it for a second. Civil engineers, they're the people who literally design and build the world we live in. We're talking roads, bridges, dams, you name it. It's a huge job, but at the absolute core of it all, there's one simple, non-negotiable rule. Things cannot be allowed to fall down. Period. And that fundamental duty is exactly why every single material they use has to be proven, without a doubt, to be trustworthy.
And this is where we get to a really key point. Concrete isn't just one thing. It's actually a highly engineered material that comes in all these different grades of strength. So think of it like this. You've got your M10 grade, which can handle about 10 newtons of force on an area the size of a pinhead. That's, perfect for something like a footpath. But if you're building a column for a skyscraper, oh no, you need the real heavy hitters, like an M60 or M70. Every single job has its own super specific strength requirement.
Which, of course, brings us to the million-dollar question. If an engineer specifies, say, M40 concrete for a critical bridge support, how on earth do they know that the stuff being poured on the construction site actually meets that grade? I mean, you can't just look at it and know, right? You have to prove it.
And this is exactly where the global engineering community really had to put their heads together. The solution they came up with is built on two rock-solid foundations. First, a universal rulebook that everyone agrees on, and second, a perfectly standardized test. So these rules are called European standards, or EN for short. The best way to think about it is like a recipe for baking a cake. If everyone, no matter where they are, follows the exact same recipe, you're all going to end up with the same cake. It's the same idea here. It guarantees that a concrete test done in Spain is done the exact same way as one in Germany. That makes the results totally reliable and trustworthy no matter where you are.
And the process we're talking about, the crushing, is governed by one very specific rulebook. Now, the full title, EN 12390-3, yeah, it sounds a little dry, I'll give you that. But this is the document. It lays out in super specific detail the exact method for figuring out a concrete cube's strength. And let me be clear, this isn't just a guideline. It's basically the law of the lab.
Okay, so now for the fun part, the test itself. Let's follow our little concrete cube on its journey, all the way from being a wet mix to its dramatic, data-filled end. And this process is incredibly meticulous. First up, the cube mold is filled up in 3 perfectly equal layers. And get this, each layer is poked or tamped exactly 35 times with a special steel rod to get all the air pockets out. Then the cube gets to go for a long swim. It's cured in a temperature-controlled water tank, usually for 28 days, so it can properly hydrate and get strong. And finally, its big moment arrives. It's placed in the compression machine and squeezed until it breaks. And this number right here just shows you the insane level of precision we're talking about. The force isn't just slapped on randomly. No, the standard demands that it increases at a perfectly steady rate of 0.6 newtons per square millimeter every single second. If you go too fast or too slow, the whole test is thrown out. It's invalid. This is all to make sure every single cube gets an identical and totally fair trial. All right, and now for the main event. The machine spits out a number, right? The maximum force that cube could handle before it gave up. But here's the thing. For an engineer, the test isn't just about that final number. Not at all. It's about how the cube failed. Because the cracks tell a story. Take a look at these diagrams. They're straight from the official rulebook. They show that there's a massive difference between different types of breaks. Over on the left, you've got what engineers call satisfactory failures. And on the right, you've got the unsatisfactory ones. Now, I know,
It might all just look like a mess of broken concrete to you and me. But to a trained eye, these patterns are absolutely packed with crucial information.
So a satisfactory failure, which often has this kind of classic hourglass shape, tells the engineer that the force was spread out nice and evenly, and the concrete mix was good and uniform. Perfect. That means the test result is valid. But an unsatisfactory failure, like where a whole side just shears off, that's a huge red flag. It could mean the concrete wasn't packed down right, or maybe the cube wasn't centered perfectly in the machine. Either way, it tells the engineer, hey, hold on, you need to look into this, because that number you got, it might not be reliable.
So, okay, the cube is crushed, the cracks have been read, we have our data. But in the world of science and engineering, a number all by itself is pretty much useless. It only becomes real, useful knowledge when it's documented and communicated the right way.
You see, the actual physical test is just one piece of the puzzle. The next step is every bit is critical, and that's writing the lab report. This report is how everything gets formally recorded, explained, and then shared with everyone who needs to know. We're talking project managers, designers, the whole team.
And a proper lab report isn't just a jumble of numbers. No, it has a very clear, logical structure. You start with the why. What was the point of this test? Then you explain the how. What was the exact procedure we followed? Then you present the what. Here are the results and what we think they mean. And then the most important part, the so what. What are the final conclusions and why does any of this matter?
And this quote just hits the nail on the head. A good report does way more than just present data. It shows that the person who wrote it actually understands the concepts behind the data. It's not enough to just say the cube broke at 50. The report has to prove that you understand what that number means for the safety and the success of the entire project. Okay, so let's pull the camera all the way back out now. Let's connect this whole detailed process from this one tiny crushed cube all the way up to the safety of an entire city.
This one single test, governed by this one universal standard, is literally the bedrock of modern construction. Every single bridge you cross, every tall building you walk into, its safety has been guaranteed by this exact process, repeated thousands and thousands of times. It's this incredible, invisible system of trust that lets us build these amazing structures that can last for generations.
So really, our world is built on this whole foundation of rules and tests that most of us never even see. This humble little concrete cube, it's just one example. And it kind of makes you wonder, doesn't it? What other invisible rules, what other careful, meticulous tests are silently working right now to hold your world together?